Okay, hello everybody. All right. So when we left off last time, we talked about glomerular filtration. We talked about structure of the glomerulus, what the parts of the filtration barrier are. So thinking about those fenestrated capillaries, the basement membrane, and those filtration slits. We're talking about how we can regulate glomerular filtration in order to make sure that we're not basically taking too much fluid out of the body or overwhelming our kidneys. So we know that we have our glomerular filtration pressures driving filtration, so movement of fluid from the glomerular capillaries into the nephron. That creates a glomerular filtration rate, which is usually about 125 milliliters per minute, but it could change substantially depending on our blood pressure if we didn't keep it in check. So we saw that we have our myogenic regulation, so a smooth muscle reaction, and helping that smooth muscle bounce back and kind of clamp down if we have an increase in blood pressure to keep our glomerular filtration in check. We had our tubuloglomerular feedback, so the fluid moving through the nephron itself. As it goes through the distal parts of the nephron, it's looping back and almost touching the first parts near the glomerulus and the renal corpuscle. So if you have too much fluid moving through those end parts, the beginning of the loop can kind of notice it and clamp down as well. So that was our tubuloglomerular feedback. And finally, we had mesangial cell contraction, which is really just kind of altering this filtration barrier using some of the mesangial cells that are kind of interspersed among these loops of the capillary. So we can basically make it a little harder for fluid to escape that capillary bed. So lower our filtration, basically by kind of reducing surface area here of the capillary. So those are ways of intrinsically regulating our glomerular filtration rate. So the situation we're thinking about, right, is what we're reacting to really is an increase in mean arterial pressure. So our blood pressure is getting kind of high, right? And we have ways that we want to stop our glomerular filtration rate from getting too high, right? So what would usually happen if we have a high blood pressure? So this means we'd have high pressure coming in to the afferent arteriole, going to the glomerulus. So without our regulation method going down this pathway, right? So that would, on its own, raise up our glomerular capillary pressure. So we'd have a higher hydrostatic pressure, the glomerular capillary. That's one of our Starling forces for filtration. So this would raise up our glomerular filtration pressure, which would raise up our glomerular filtration rate, but we don't want that to get too high. So with our regulation mechanisms going down the other side, we're creating basically negative feedback on this process. So when we have that rise in pressure in the afferent arteriole, for our myogenic regulation, what that's doing, right? That increase in pressure in the arteriole is expanding those arterial walls, right? Stretching them out. They constrict back down. So constricting, increasing resistance, which means now we're going to have a little less flow there, which means we're also going to have less pressure. This is a negative feedback on that initial rise in pressure. The tubuloglomerular feedback works similarly in that it's also negative feedback. Right, so we have the same situation we're trying to fix. We had a rise in arterial pressure, creating a rise in glomerular capillary pressure, rise in glomerular filtration pressure, and therefore a rise in the glomerular filtration rate. Right, so absent any regulation, this would basically mean you might end up peeing out a ton of fluid, right? That's kind of why we don't want this to happen. Okay, so what we do with our tubuloglomerular feedback is that we're noticing we have that increase of flow out of the nephron, basically. So the macula densa cells notice this. They secrete basically kind of like some local hormones. So paracrine signals are just kind of like local signals to those cells in the glomerular capillary. So they're going to cause constriction in that afferent arteriole, increasing the resistance of the arteriole. So we're lowering flow to the glomerulus and therefore dropping down that glomerular capillary pressure. So this is another way that we are keeping that glomerular filtration rate from going up and up and up and causing us to lose too much fluid. So those are both intrinsic methods of regulation. So they're local to the kidney. They're from the kidney, coming from basically the structures of the nephron itself. But we do also have some extrinsic controls here on our glomerular filtration rate. Okay. So this is a reminder that we have a relationship between the mean arterial pressure and that glomerular filtration rate. So absent anything else, if your mean arterial pressure goes up, your glomerular filtration rate goes up. But we create this nice plateau in the center here by using our regulatory mechanisms to prevent our glomerular filtration rate from skyrocketing way too high in relatively normal blood pressure ranges. Okay. So in terms of our extrinsic control, basically, we're also going to see that the nervous system can have an effect here as well. Okay. So we're going to be more interested in this when we think about our decreases in blood pressure. So a decrease in blood pressure could take us down this line, right, and decrease our glomerular filtration rate. Okay, so we're going to want to be able to regulate that as well. Okay. Those decreases in blood pressure would both directly have an effect on that glomerular filtration rate, and then they would also indirectly have an effect through some of these extrinsic controls. So let's take a look at another situation related to basically like fluid loss here. Okay. So a reason you might have a drop in blood pressure, right, would be something like if you're bleeding out, right? If you have hemorrhage, you're physically losing blood, right? You have less fluid in your vasculature. So less fluid would also be going to your kidney. If you're sweating a ton, right? That fluid has to come from somewhere, right? So this could also actually drop down your blood volume a fair amount. Okay. So if we have a drop in blood volume, then we're going to have a drop in the venous pressure. We'd have a drop in our mean arterial pressure coming out of the heart and pumped into the aorta, right? Okay. So we know that a couple things. One thing, we've just learned that a decrease in our mean arterial pressure would decrease our glomerular filtration rate, just like an increase in mean arterial pressure would increase that glomerular filtration rate. And from before, we also know that we do have mechanisms of sensing changes in blood pressure, right? When we talked about the cardiovascular system, remember that we had our baroreceptor reflex, for example, as a way of kind of correcting sudden drops in blood pressure, right? So we have these baroreceptors that can detect and respond to changes in blood pressure, and therefore also basically respond to changes in blood volume. If we're thinking about reacting to sudden blood loss or intense sweating or something like that. Okay. So when we notice a drop in blood pressure, a drop in MAP, because these baroreceptors are sensing that and sending signals to our central nervous system, the ultimate effect is that our sympathetic nervous system gets activated. Okay, so we increase sympathetic nervous activity in response to this drop in mean arterial pressure. And basically, this also sends a signal to the kidneys. So your kidney also gets sympathetic innervation. So you have sympathetic nerves going to the kidney. Okay? And one of the things that those renal sympathetic nerves are going to tell your kidneys to do is to increase the vasoconstriction of both the afferent and the efferent arterioles, which creates a lot of resistance. Okay. And this might seem counterintuitive, right? You might think, okay, but that's going to make the situation worse, right? Like we're continuing to decrease the glomerular filtration rate if we're increasing this resistance here, which would be true. But ultimately what we're trying to fix, right, is we're trying to fix this fluid loss in terms of like, we're going to try to stop losing fluid from our blood, right? We're going to be trying to maintain blood pressure, right? So it's actually kind of good that we're decreasing our glomerular filtration rate here, because this means we're going to pee out less fluid, which means ultimately our biggest bonus from this process is that we're going to keep that fluid rather than peeing it out. You're going to keep it in the blood. And so that's going to help us kind of ultimately pull that blood pressure back up by just like not losing any more fluid from this region where we usually would be excreting some of that fluid as waste. So it's all tied in with our other regulatory mechanisms, which is why when we talked about regulation of MAP, we mentioned that the kidneys are going to be part of it in the long-term regulation, right? This is that part basically. So the kidneys change how much fluid you lose as urine, right? And so if you keep that fluid, it just stays in your system. And so you keep blood volume up and can keep blood pressure up if it's dropping too low in the long run. This brings us to reabsorption. So we have a lot of fluid getting filtered out of the glomerulus and into the nephron as filtrate. So we've got water, we've got some ions in there, we've got everything basically except for proteins, anything involving cells getting into the nephron so that we can determine what we want to keep in our body and what we want to get rid of. Okay. So as we move from the renal corpuscle, so the glomerulus and Bowman's capsule, into our proximal tubule, we're really going to be thinking a lot about this process of reabsorption. So filtration, we had movement from the glomerular capillaries into the nephron. For reabsorption, we're going to be moving stuff from that filtrate back into the body. So we're going to be reabsorbing it. So it's going to be going from our tubules, first the proximal tubule, but we'll see later on, we have reabsorption going on in some other regions as well, into a different set of capillary beds. So we don't usually draw them on, but when we draw a nephron, right, we have our Bowman's capsule, so our renal corpuscle, that kind of Pac-Man head of the nephron, and we have our proximal tubule, right, loop of Henle, distal tubule, joining up with our collecting duct. Okay. What we're not drawing on is the fact that we have blood flow parallel to this, basically. It doesn't always run in exactly the same direction, which we'll talk about as we talk about how we make the inside of the kidney basically really salty. But we do have additional blood vessels called paratubular capillaries, basically on either side here, right? So we have more blood here. Okay, so this is separate from the glomerulus, which is where we were doing our filtration, right? So what I'm saying here, filtration happened from the glomerular capillary into the nephron. So that was our filtration. Reabsorption happens from the filtrate into those paratubular capillaries. Okay. So most of this reabsorption is going to happen where I've drawn it on here in the proximal tubule. So most of it is not going to be regulated. So this is just going to be basically a natural process. You're not going to need the involvement of a bunch of like hormones or nerves or extrinsic kind of signals for this reabsorption to happen. Definitely not in the proximal tubule. When we get to the adjusting and fine-tuning part near the end of the nephron, we are going to see that we will have regulatory mechanisms helping us determine the final content of urine. So in terms of what we physically need to cross in order to reabsorb something, right, we're going to have to cross the wall of the nephron. So we're going to have to cross renal epithelial cells that form basically the edges of the tube, right? And then we're going to have to cross the blood vessel that we're going into. So those peritubular capillaries are lined with endothelial cells. So we're crossing their walls as well on our way back into the systemic circulation. So these are our barriers for both water and other solutes that will be reabsorbing in the proximal tubule. So we're going to take back a bunch of water. Okay, so lots of water. So we filter 180 liters per day of water, meaning it gets into the nephron as filtrate in the first place. But we are going to reabsorb 178.5 liters per day, which is why you're not, dying immediately because your kidneys are functioning, right? So we have this water coming back into your body, staying in your bloodstream, keeping your blood volume up. So that's good. But we have other things that we want to keep around in the blood as well. So glucose is a really important one. We do filter 800 millimoles of glucose per day. So it gets out of the glomerular capillary, goes into Bowman's capsule, ends up in the proximal tubule. But we want to reabsorb it, as much of it as we can. So usually we reabsorb 100% of that glucose that we're filtering. So the filtered load, remember, was just we're multiplying the glomerular filtration rate by the concentration of that freely filtered substance. Okay, we did that calculation last time. There are other things we are also reabsorbing to various degrees. So here we can see that really a lot of our ions in particular, right, are going to have pretty high rates of reabsorption for those. And most of this is happening in the proximal tubule as well. Okay. So reabsorption in the proximal tubule is not regulated. So we are not going to be responding to hormones, nerves, all that stuff. We're kind of just doing it. Okay. So we think about our proximal tubule as our mass reabsorber. And the reason for that is it's doing most of the reabsorbing. So about 70% of the sodium and water are getting reabsorbed here in the proximal tubule. And all of the glucose is getting reabsorbed here. So it's doing a lot of reabsorption. That's kind of its like primary job for our proximal tubule. So if we were to look at the cells lining the proximal tubule, those renal cells are going to have a particular kind of shape to them in order to make this process work. Okay. So one thing is they're going to have a really nice big surface area. So we have what we call a brush border to these cells. Right? So this brush border on the apical side, so the side facing the lumen of the tubule, so the side like facing the filtrate, the stuff that's going to become urine. We have lots of projections, so lots and lots of surface area. So hopefully we have lots of room for the substances going through the nephron to run into the membranes of these cells in case we want to suck them back up. Okay. And the other thing that is true is that some of the things that we're going to be reabsorbing are going to squeeze in between our cells. So we have some kind of leaky connections between the cells in our proximal tubule. So we got kind of a leaky membrane here because of these leaky tight junctions. Let's take a look at how reabsorption would work. Right? So we have some filtrate coming down from our glomerulus. It's going through our nephron. It's passing through our proximal tubule. Okay, so that's our tubular fluid or our filtrate going through here. So this would be the lumen of the nephron, right? Lumen just meaning the hollow part of a tube. Here we can see that nice foldy apical membrane, right? That brush border with the microvilli, creating lots of nice surface area. So we're going to have to cross into the peritubular capillaries by crossing first our renal tubule cell, so this epithelial cell. Okay. It's going to be a little bit of peritubular fluid here. And then we're just going to cross into our peritubular capillary by crossing its endothelial cell layer, basically its wall. Okay. Should hopefully not be surprising that often this is going to rely on things like sodium gradients. So what we're looking at here is how reabsorption of glucose works. Well, part of how reabsorption of glucose works, right? So we're going to see that we have sodium-potassium pumps driving sodium gradients, right? So creating a sodium gradient across the renal tubule epithelial cell. So when we have a sodium-potassium pump, right, this means that we're taking sodium, moving it against its concentration gradient. We're doing the same thing with potassium. So basically, we're creating low sodium inside the cell and then higher sodium outside the cell. Okay. Right. And so when we're reabsorbing glucose, this means that we can use that sodium gradient now. We've created a low sodium environment inside our renal cell. We can use it to do secondary active transport and pull our glucose molecules in to the cell, and then we'll ultimately pull them back into the peritubular capillary as well. I'll take a look at some more examples of this, but that's what we're doing overall. And we're going to be thinking about glucose for a bit. So looking at that image or thinking about that image, I want you to imagine that that sodium glucose transporter takes like a second to move a single glucose into the cell. We've got lots of filtrate flowing past. So what do we think is going to happen if instead of just having one glucose traveling along through the filtrate, we have three passing by the cell at the same time? All right, take another second or so. I'll take a look. All right. So this was a prediction question. So we're going to talk about it. But yeah, so what we're going to find that's going to be true about transporters in the proximal tubule is basically they should be able to reabsorb 100% of the glucose that you have coming past. But like when we spoke about enzymes a long time ago, right? They're just proteins. They can get saturated, right? You might not have enough glucose transporters to move all of the glucose back into the body. So you reabsorb it into the peritubular capillaries, not into the glomerulus. So it's this different region of our cardiovascular system. Okay. So they're going to have this property where they're able to be saturated, which means that if you have really high glucose levels in your blood to begin with, you end up with really high glucose levels in the filtrate going through your nephron, then at a certain level, you're going to be giving your kidneys as much as they can handle. And you may end up with spillover into the urine, which is why one of the early tests for diabetes was like checking whether urine was sweet or not. Because we should be reabsorbing all the glucose, but under certain conditions, we can't. Okay, so this takes us to the concept of transport maximums. Okay. So transport maximum is just the rate of transport when our carriers are saturated. So what we're saying is that our carriers, right, are proteins embedded in the membrane of a cell. And at a certain rate of flow past them, right? So like once you have a certain amount of glucose flowing past these transporters, you've hit that maximum rate at which they can accommodate everything. They get fully saturated, and then any extra is just extra, and you're going to pee it out. You're going to excrete it out more formally. Okay. So this takes us to a related kind of concept. So the renal threshold for a solute that is normally completely reabsorbed, so 100% of it is reabsorbed. That renal threshold is basically another type of measurement of that amount where we're creating this full saturation of our transporters and would end up with the spillover into the urine. Okay, so we'll take a look at how we kind of compare these numbers in a second. But glucose is always going to be our classic example of this because diabetes is relatively prevalent, right? You probably work with it or know someone who has it. If you talk about healthcare pretty much at all, glucose gets freely filtered at the glomerulus, so we have lots of glucose getting into the nephron. It should be 100% reabsorbed into your peritubular capillaries as it flows through the proximal tubules, and none of it should be spilling over, but it might happen if we hit this threshold here. Okay. So what we were looking at on the picture earlier, we're looking at that secondary active transport of the glucose on the apical membrane. On the basolateral membrane, we would allow glucose to just diffuse through a protein, but we wouldn't need any energy on the basolateral membrane. So we'd have facilitated diffusion on the part of the cell that's facing the blood. Okay. So here we can see that drawn out again. Okay. Now we're looking at some numbers as well. Okay, so here we see that apical membrane with that secondary active transporter for our glucose. And we can see it's using that sodium gradient. Here we see that facilitated diffusion of glucose. And then glucose is actually just kind of squeezing into the capillary here on the other side. So remember in these diagrams from your textbook, when there's a green arrow, it's telling you that's a passive direction. That's like with the gradient. If there's a red arrow, it's telling you that's going against a gradient. Okay. So we can see that we had to use energy to get glucose into the proximal tubule renal epithelial cell, but to get glucose from that cell into the capillary, we didn't have to expend any energy. Okay. All right. So normal plasma glucose is about 100 milligrams per deciliter. And we calculated last time the filtered load of glucose is going to be 125 milligrams per minute because we're just multiplying it by that 125 glomerular filtration rate. Okay. Now the transport maximum for glucose is 375 milligrams per minute. So that's how much glucose, right? Like this is like our rate, right? Like how many milligrams we can physically reabsorb into the body per minute using our existing glucose transporters here, right? So that's the most we can do. So this is going to correspond then to an actual like blood plasma level of glucose, right? So theoretically, you shouldn't hit this transport maximum until you get to about 300 milligrams per deciliter in the blood of glucose. You find that because your glomerular filtration rate times the renal threshold is going to give you this transport maximum. Okay. However, in reality doesn't match theory all that well. So our actual observed renal threshold is going to be more like 160 to 180 milligrams per deciliter. So what that means is, right, like theoretically, we shouldn't see glucose spilling over into the urine until we hit that renal threshold, that theoretical renal threshold of 300 milligrams per deciliter. But in practice, not all the glucose in the filtrate perfectly matches to every available transporter in the proximal tubule. So we actually end up with glucose making it through the nephron without being reabsorbed at much lower levels of plasma glucose. So in practice, you should be able to reabsorb this much glucose, but kidneys don't work perfectly. So at this lower actual renal threshold is when you would start to see spillover into the urine. So the renal threshold, we're thinking an amount of glucose in the plasma that corresponds to the saturation. The transport maximum, we're thinking about like amount of glucose per minute that we can reabsorb. So basically the difference is that one of these is a rate and one of these is just like a measurement of your blood glucose. But concept for both is the same, just different ways of kind of thinking. So what's happening here, right? If we piece together some of our different concepts, right? So glucose is freely filtered at the glomerulus. So we're looking at the rate of glucose moving relative to how much glucose there is in your blood, right? So rate of glucose versus plasma concentration of glucose. If you have more glucose in the blood, right? So as plasma concentration of glucose goes up, so does the rate of filtration of that glucose, right? So more glucose flowing to the nephron, more glucose getting into the nephron. Okay, so that's why we have just a straight line here, like a one-to-one relationship, because we don't have any changes to that barrier for filtration when we're thinking about glucose. It can just go straight through. Okay. So until we hit our renal threshold, and this one is labeling our actual renal threshold because so you'll presumably be interacting with actual people. So we're just gonna use that 180-ish number here. Okay. So until we get to that renal threshold, as much glucose as you filter, 100% of that is getting reabsorbed. So our lines for filtration and reabsorption match until we hit our renal threshold. So that renal threshold of 180-ish milligrams per deciliter for our plasma concentration of glucose. So if you're reabsorbing all the glucose that you're filtering, none of that glucose is getting excreted. So excretion is when you're peeing stuff out, right? So excretion, removing stuff from the body. Okay. So excretion is going to be 0 so long as filtration and reabsorption are matching each other. But at that renal threshold, right, this is where we start to see saturation of those transporters, right? So basically what we're saying is that we can't keep up, right? The reabsorption can't keep up. So this line for reabsorption back into the body starts peeling away from our filtration line, right? So if we're not reabsorbing all that glucose that we're filtering anymore, it's got to go somewhere. And where it's going is into the urine and it's getting excreted. So we're matching up, right? This missing piece, the stuff we'd like to be reabsorbing, is now here and getting excreted out. So those are matching up here, right? So once we see a flattening out of that reabsorption rate, right? Reabsorption rate, our transport maximum is a rate, right? So that transport maximum, right? We see here at about 375 here. That's the maximum amount we can ever, no matter how much glucose we get into the nephron, that's the fastest we can absolutely reabsorb the glucose. So that's the relationship between these concepts, right? So at the transport maximum, we see the maximum amount of reabsorption that we can possibly do using our existing glucose transporters. It's at the renal threshold that we start to see less reabsorption happening than filtration, because we're starting to kind of saturate those glucose transporters. Said this out loud before. All right. So the other thing that we want to remember that we are reabsorbing a lot of is water, right? So 180 liters of water is getting filtered per day, but only about 1 to 2 liters are going to get excreted as urine. This is good. We don't want to lose all that fluid. We don't have that much fluid. The other part is getting reabsorbed, right? So we're still thinking about reabsorption. Okay. So reabsorption is when we return molecules that we've filtered out, and we're returning them to the blood. This time we're thinking returning to the peritubular capillaries. Okay. We have 180 liters of water going through your kidney per day. Only 1 to 2 are actually going to your bladder and getting excreted as urine. If you drink a lot of extra water and you're really well hydrated, then you're going to increase the amount excreted as urine. If you're dehydrated, you're going to keep that fluid in a little bit. So you might excrete less urine, but we are going to have a minimum amount that needs to be excreted in order to get rid of all your wastes. So we're thinking like metabolic wastes. So you need about 400 milliliters of fluid just to have all that stuff dissolved in something in order for you to actually urinate it out. So we think of 400 milliliters of this as your obligatory water loss. So it has to be lost. Most of this reabsorption is happening in this proximal tubule. Okay. Reabsorption happening in the proximal tubule. And then we'll have some more water reabsorption happening in the loop of Henle, particularly in the descending loop of Henle. Until we get to the final parts of the nephron, we do not have regulation of this process. Okay. So when we're thinking about our water reabsorption in the proximal tubule, okay, we want to think about the fact that we do have solutes dissolved in the water. Okay. So the main solute that we have here in the water is sodium. All right, so sodium, you got a bunch of sodium in the filtrate. It's coming through because you had a bunch of sodium in your blood getting filtered out of that glomerular capillary. Okay. That sodium is going to get actively transported back into the body. So we saw that active transport in the form of the sodium-potassium pump on the basolateral membrane as we were looking at the situation for glucose. Okay. So sodium is getting actively transported. We're using energy, and we're establishing a gradient for water reabsorption. So that sodium basically is going to be pulling water towards itself now that we have sodium building up away from the walls of the proximal tubule, basically. So when we think about water movement, we want to think about where are the salts going, where are the ions going. Water is generally going to follow them in order to keep everything at equilibrium, even out those gradients. Okay, so I'll take a look. All right, so when we have filtrate coming into the Bowman's capsule out of the glomerulus, we're starting out with a situation where we have an isoosmotic setup. So what we're saying there is concentrations of everything in the blood, in the plasma, are the same as the concentrations in filtrate, right? So same as where they're in Bowman's capsule. But then we start to actively reabsorb that sodium. Right? So we're actively transporting sodium into the peritubular blood. Right? And now we're going to set up a gradient. Where's, I wish they would. Okay, we're going to do this one. Okay, so actively transporting sodium or other solutes, but really we're thinking sodium into the peritubular blood. So now we're creating a situation where we're no longer in this isoosmotic setup. We now have a difference in the solute concentration in that peritubular blood versus our fluid next to the peritubular blood, and especially relative to the fluid going through the proximal tubule. So this basically sets us up with a situation where we're ready to drive osmosis. Fundamentally, what's happening is that the movement of a bunch of solutes into the peritubular blood, so think like sodium over here in the peritubular capillaries, but also some other solutes, is going to pull water from the peritubular fluid into that capillary. Okay. So this is one of the ways, this is really the main way that we are creating a situation that's set up for water reabsorption to happen in the proximal tubule without like any hormones involved or extra steps, right? So this non-regulated portion. Okay. Now, we do have active transport of some things happening here across the walls of the tubule, right? Across this renal epithelial layer. Okay. So we have tight junctions attaching our cells to each other, right? So here we see our tight junctions. We know that we have microvilli on the apical side of these membranes, right? And we know we've created a low sodium environment inside these cells, low sodium, okay, by actively pumping sodium towards our peritubular capillaries, okay, right? Because we had these pumps on our basolateral membrane, okay? So we were able to do secondary active transport of glucose across that apical membrane, okay? And we're also going to be continuing to pump that sodium and that filtrate kind of past the other side of this membrane as well. So we got all moving through here. So because we're pumping sodium all the way through into this peritubular space, right? So we're having relatively high sodium here in the peritubular space. Okay. High sodium here. We had low sodium here. Okay. We're also going to end up drawing negative ions towards that high sodium. So particularly chloride ions with their negative charge, these anions are going to be attracted towards those sodium ions. So now we're ending up with a collection of sodium ions and chloride ions in this space, right? So now we're ending up with like a really high concentration of things dissolved in the water on this side of the cell. Okay, so water is moving towards both of these kind of at the same time. So we end up with a bunch of water reabsorption moving first towards this peritubular space and then into the neighboring capillary. So here we see the reabsorption of these various components, right? So here we're looking at that sodium-potassium pump, right? So creating sodium gradient across the cell, high sodium concentration here. We would also be pulling chloride ions towards this space because we have an attraction of the charges. And overall, this draws water towards this heavily concentrated region. I have a question for you all. Is this what came next in your slides in your copy? It is? Okay, good. Sorry, I saw some very fast writing and I was suddenly worried that I'd opened the wrong slide set for you. Okay, good. All right, so when we're thinking about this salt and water reabsorption, we have active transport of the sodium, right? So active transport, main thing we want to know about that is that we have that sodium potassium pump on the basolateral membrane, okay? So we're using energy for that. Chloride ions with their negative charges are following through, basically through passive transport. We're having those negative ions attracted to the positive charge on the sodium. Okay? Now we've basically got a lot of salt neighboring the peritubular capillaries and neighboring the proximal tubule. Okay, so water is now going to follow those salts by osmosis because water likes to go where there isn't enough of itself. It's going from its higher amount of water here in the filtrate to this relatively lower amount of water where we've built up these chloride and sodium ions neighboring the proximal tubule. Okay. All right. So when we're thinking about reabsorption, we do want to remember that the proximal tubule is our mass reabsorber and is doing unregulated reabsorption because we are going to talk about what regulation of reabsorption looks like later on. So I want to make sure that we got a good understanding of what that means, unregulated reabsorption. Okay, let me take a look. Okay. Yeah. So when we're saying unregulated, this is what I just wanted to check for. Looks like we're most on the same page. When we say unregulated, we mean that we're not doing any fancy fiddling with hormones and stuff at this juncture. It doesn't mean that we don't need energy. We do still need ATP and stuff for these processes to run. So that sodium potassium pump uses ATP, secondary active transport of glucose. It's using the sodium gradient, right? Secondary active. So there was energy in the form of ATP involved there. So we do still use energy. We're just not doing regulation. Okay, perfect. All right, so we'll pick up here next time.